Yesterday, we reviewed what a function is. What we're going to talk about today, which is the last piece of our lesson from yesterday, is a notation that you can use with something if it is a function. If something is a function, it can be in different forms. So you've already looked at some different forms. We can put our function in a table. We can put it on a graph. We can make a mapping for it. Functions also have equations that can be written that represent the pattern if a function follows a predictable pattern. So this equation, y equals 3x plus 4, this is the equation for a function. It actually is a linear function. If you were to make a table and a graph, everything would line up in a straight line. We already know from working with graphs and working with relations that x is the domain or the input. And we already know that y is the range or the output. So basically, I would fill a number into the input, and it would give me an answer, which is the output. Function notation still uses inputs and outputs. It just changes what this looks like a little bit. In function notation, this exact same equation would look like this. The way that we would say this, if you were talking about it out loud, would be to say f of x equals 3x plus 4. What we changed was right here. Instead of using y for our output, now we're using this thing, f of x, to represent our output. So this has two pieces to it. The f is the name of the function. You could use any letter you want to name your function, and you will see functions with different names. So you might see a g of x or a of x. It doesn't really matter what you use. A lot of times people like to use f because f stands for function. And then this is still the input. So basically what this is telling us, whatever number is right here, is telling us to take that number and use it as the input in function f to get an output. So it's very, very similar to our starting equation. Again, the red highlighted piece is the only change that we made visually. We still work with the function the same way. So we would still put an input in for the x, and we would still get out the output that goes with that. So a generic outline for function notation would look something like this. Again, I'm going to use, well, we'll be generic. So it looks something like this. This is where we would have the function name. This is where we have our input. And then the other side, the expression over here, tells us how to get the output. So it's telling us what to do with the input to get the output. So in the example we were just looking at, it would be telling us take the input, multiply it by 3, and add 4, and that gives you your output. So coming back to our y equals 3x plus 4, or in function notation, f of x equals 3x plus 4. if we wanted to use that notation, it would look something like this. So you can be given an input in function notation that's asking you to calculate the output based off of that input. So maybe I might be asked to calculate something like this. If I'm asked to find f of 2. So what this is telling me is to use an input of 2 in function f. So since it just told me use function f, use an input of 2, I can come up to my function f, 3x plus 4, and I could say, okay, so to figure that out, I'm going to fill in the input of 2 into the function so that I can figure out what my output is. 3 times 2 is 6, plus 4 gives me 10. So f of 2 equals 10. In other words, if I use an input of 2 in function f, I will get an output of 10. The reason why we have function names is so that if we're working with multiple functions at once, we could tell them apart. So we're going to grab the same function we've been using. But now we're going to add another function in with it. Maybe I have a second function that follows a different pattern. Maybe I have another function that does this. Well, I want to be able to tell that apart from function f. If I were using a y instead of using function notation, and I asked somebody to fill an input into the function, they wouldn't know which function to use. So that's where function notation comes in handy. It can help you be more clear if you're working with multiple functions at once. So I can change these y's, change it into function notation, and call this function f. And I can give this other one a different name. I'll call it function g. So now that these have names, you can very specifically reference those names. So maybe if somebody gave you an input, if they gave you something like this, g of 3. So previously, you would have just had an input of 3 and you wouldn't have known without the function notation which function to fill this into. But because I'm working in function notation and I can see the names of the functions, I know which function I'm supposed to put that input in. Function g. So that tells me, okay, I need to come over here and use this function. So then I could go ahead and fill that input into the function, since this is telling me use an input of 3 in function g, and I could figure out, okay, if I put in a 3, I get out a 5. So that's where function names are useful. If you're working with more than one function at once, you can use your function notation to help people know which function you want them to work with at any given time. There are a couple of other things that you can do with function notation with inputs and outputs that look a little bit tricky, but they actually aren't too bad if you're paying attention to what your notation's telling you. So in this case, g of 3, we were filling in a number for our input. Since we were filling in a number for the input, we were able to get out a number for the output. Down the road, you guys will look at some situations where you might not be filling in a number for the input. You might be filling in an expression for the input. And you guys will learn why we might do that later on. But for now, while we're talking about function notation, it's good to be aware that that's something you can do. So maybe you might be given something like this. So this is telling us to use function f. So we know that what we're filling into function f. But now our input's not a number. Our input is an expression. So we could still drop that into the input slot. So function f tells us to take the input, multiply it by 3, and add 4. It doesn't really matter what the input is. Whatever I've been given, I can multiply it by 3 and then add 4. So if I'm given an expression as my input, I can still take that expression, multiply it by 3, and add 4, just like I would if I was working with a number. The only difference is because this is an expression, I can't actually evaluate it. I've got a variable in here that's getting in my way, but I can simplify it. If we use some distributive property, we could rewrite this. And then associative property says I can add in any order I want, which means I could add the 3 and 4 together. And I would get this. So f of x plus 1, in other words, if I put an x plus 1 for my input, equals, or gives me the output of 3x plus 7. So generally, if you put in a number, you will get out a number for your output. If you put in an expression, you will get out an expression. So you can put anything in for your input that you want, but whatever you put in for your input, you're going to get that same type of thing out for your output. Put in a number, get out a number. Put in an expression, get out another expression. But that's a nice thing that you can do with function notation, is that you can basically feed anything you want into your function, and this gives us a way of communicating that. So it gives us a way of saying, put an x plus 1 into function f. So function notation gives us some very specific ways of showing that. You could, and this would be a challenge level problem, but it's good to think about to keep you challenged. You could even do something kind of tricky, and you can put functions inside functions. So you might see something like this. Maybe you might see something where you're asked to find f of g of 1. Well, order of operations says to do parentheses first, right? So if we start in the parentheses, we would have to start here and figure out what g of 1 is. So this is telling us to put an input of 1 into function g. So if we come over to function g first, to get the output, we have to do 2 times the input minus 1. So that means if I put in a 1, I get out a 1. So then I could come back to my original thing and say, okay, so g of 1 has an output of 1. So I could replace that inside my parentheses. Now it looks like that. But now what this is telling me to do is say, okay, you found what was going on in the parentheses, but now you're going to take that and you're going to turn it around and you're going to run it through another function. So the output from function g turns into the input for function f. So now I would take this, f of 1 is telling me to use a 1 as the input for function f. So I could come over to my function f and say, okay, I'm going to put a 1 in for function f. Function f tells me to do 3 times my input plus 4. So that would give me 7. So this whole thing has an answer of 7. Again, this would be something that would be a good challenge problem or bonus problem. It's very doable. It's just using the same steps we've been talking about twice in a row following order of operations. So it looks kind of tricky, but it's not so bad if you take the time to follow your order of operations and break it down one step at a time.